Hello everyone, this is Selman, and this is the first presentation in the series of final presentations for the course Physics 58E of Boğaziçi University, Fall 2020. And my topic for today's presentation is micromagnetics. First of all, I'm going to talk about the aims and the scope of micromagnetics, and then delve into physical theory necessary to be built for micromagnetic studies and some example implementations. First of all, let's discuss what micromagnetics is. It is not an experimental or theoretical study, but it's rather a numerical computational study. So basically, when you hear micromagnetics, what should be thought is a simulation study in general. But a simulation study involving nano devices making use of magnetic phenomena. And the primary reason for employing micromagnetics is, of course, to reduce the cost, because building such nano devices is extremely costly. And now, as an example of a magnetic technology, there's a picture of a hard disk drive. On the left, there's the surface texture, and on the right, there's the magnetization of a really small 20 to 20 micrometer wide area. And in order to, for example, develop this hard disk, or before building prototypes, before building expensive manufacturing systems, we have to analyze, for example, how fast is it possible to alter the polarizations of these bits, or how dense can we store these bits in that material without those bits interfering with each other. In order to do these example applications and many more in research, we need micromagnetics. And there's a more prominent example of micromagnetics use that's in research use. This, for example, here is a spin hole nano oscillator novel device design by group of Giovanni Finocchio, and these names may be familiar with for most of our research group, because these people were our previous collaborators. And you see here the result of micromagnetic study. You see the arrows which correspond to local magnetization vectors, and these evolve with time. And what matters in this study is to watch the evolution of magnetism with respect to time in order to validate the device without actually building it. And the exact scope of micromagnetic simulations is a dynamic rather than static simulation. In order to do any kind of simulation study, whether it's a social economic simulation or some technical simulations, we need to define the abstract scope of the simulation study. And micromagnetic simulation investigates the system's behavior in time. Therefore, it's a dynamic simulation. And it's also a continuous simulation. That is, the functions we investigate, which is the distribution, which is the magnetization vector dispersed in the material, it should be a continuous function of both time and space. Actually, you may say that it is in reality somewhat quantized, with dipole moments being placed on certain points in the crystal lattice. But we do not work at that scale, and we have something called continuum approximation, which obviously means that this function is assumed to be continuous, and we work at a scale in which it seems continuous. And lastly, it's a deterministic simulation, not a stochastic one. And this one means that the evolution of the system in time does not include any randomization. Think of it like just a simulation of a Newtonian mechanical system where the force is determined. You just integrate the effect and find how the object moves in space with respect to time. But this, although it sounds good to have a deterministic simulation, is actually downside of most simpler implementations of micromagnetics, because we sometimes want to investigate effects of temperature, and effects of temperature are basically stochastic in nature. So we keep defining the micromagnetic scope, and the scale of micromagnetics, spatially it's about 1 nanometer, it works about 1 nanometer scale, because the device is built and the phenomena observed, like formation of magnetic domains in a ferromagnet, as the simplest example, the features are slightly larger than this order of magnitude in size. But their evolution in time is quite fast, and we observe, for example, around 10 gigahertz of signals from such dynamic behavior of ferromagnetic systems. And we need to resolve from nanoseconds to picoseconds, depending on what exactly we want to find out in micromagnetics. And things not taken into account in micromagnetics include atomic origins of interactions. The strongest example of such physical effects is exchange interaction in a ferromagnet, of course, but micromagnetics has nothing to do with what causes this exchange interaction, which is quantum mechanics in reality. We need to do some quantum mechanical simulation in atomic to subatomic scale in order to find it out. The micromagnetics used results from such computations, or more dominantly experiments, and plugs it into some equations to determine the behavior at larger scales than this. And also, thermal or stochastic effects are not considered in some implementations, though some more advanced ones do include them. Then, what we arrive at what we should be given as input to a micromagnetic model and get as output. The output, as we discussed just previously, is the distribution of a magnetization vector. So it's a vector field, magnetization vector, and it's time-dependent behavior because it's a dynamic simulation, and in many cases, actually most cases, we want to see, what we actually want to see is the dynamic behavior of this system. Therefore, what we get is a distribution of tiny magnetic regions, magnetizations, with respect to time. And our inputs are, of course, dimensions of the system, including boundary conditions. For example, in this study, it is just a rectangle. And then magnetic properties of the matter as abstracted, like saturation magnetization value, exchange energy, and anisotropy, if any. And then external magnetic fields, and sometimes spin currents of external origin as well. And of course, some simulation parameters like cell sizes. We cannot supply the micromagnetic system with the material type itself in general, because as we taught, what micromagnetics does is to assume these interactions and calculate a result. As an example output, as an example application, you see here the evolution of a secure muonic logic device. This is a majority gate, and you see here these secure muonic structures, which is a vortex-like structure, topology of magnetization in the materials, moves to one state and they interact, merge with each other to give some outputs. This is a very good example of a micromagnetic study. And now that we define the scope and the necessities of micromagnetics, let us define what exact physical phenomena do we have to consider in our calculations in micromagnetics. First of all, we start with macrospin dynamics. In spin dynamics, when a spin is put under influence of a magnetic field, it does not simply point to the direction of that magnetic field as in a compass. It precesses around it. Even a simple compass doesn't just point to the magnetic field's direction. It actually oscillates around it. So there's a dynamic behavior, and this dynamic behavior in spins is actually a precession, which is quite similar to a simple spinning top. Because in a spinning top, there is there's an angular momentum pointing this way, I guess if the camera doesn't mirror me, and there's a torque which is perpendicular to both the vertical axis and the angular momentum itself. Therefore, instead of changing the magnitude of the angular momentum, it just makes the angular momentum revolve around the z-axis here. Because it is also the torque, so the change in angular momentum is also perpendicular to z, it never approaches z, it just keeps precessing. This is a very simple device, it's a very simple physical example, but it manifests itself as the primary reason of spin dynamics behavior. And gyromagnetic effect here describes why spins behave exactly in the same way or a very similar way to a simple spinning top. It is because it has a magnetic moment and an angular momentum associated with it, and they are related to each other. So a magnetic field, by creating a perpendicular torque in the same manner the gravity creates a torque in a spinning top, but it does not really alter the size of the angular momentum, which like the magnetic moment itself is perpendicular to this torque. And in this case, we have a spin and associated angular momentum and magnetic moments, and then H field, some kind of caused by whatever, and this H field causes it to precess. Let's derive it simply. dl dt equals the torque. It is any case, but in this case, the torque is caused by the interaction of magnetic moment with an H field, if we are in CGS units, of course. And then in this case, we have this L, which is simply related to the magnetic moment as with gyromagnetic ratio, as I just described. And then we get that the magnetic moment makes a simple precession. And then when we consider all the magnetic moments in a tiny volume, in which we can assume they are dispersed homogeneously and they are all pointing in the same direction, which is quite precise for a ferromagnet, then we get this equation relating magnetization's change in time. And then we see that this is identical to Larmor precession. This is the name that is used more commonly in nuclear magnetic resonance, and this is ferromagnetic resonance, as we do experiments with it. And this torque doesn't change the magnitude of the magnetization, which has to be the same anyway, because we are in a ferromagnet. So in the scale we are at, the magnitude of the local magnetization of a ferromagnet has to be the same everywhere, except in some rare cases and temperature dependence, of course. And now let's generalize this equation by adding a damping term. We need this damping term because it cannot, of course, precess forever. And because of some reason, which is not identified now, which we don't have to identify, it has to be converging in time into its most stable state of pointing parallel to the magnetic field. And in reality, we know that the reason for this damping, the primary reason for this damping, alongside many others like simple radiation, is a spin-orbit coupling. Therefore, we see this effect, this damping effect, much more pronouncedly in heavier species like platinum or tantalum, because the spin-orbit coupling strength or energy, which defines its strength, scales with cube of the atomic number of an atom. And now let's add this damping term, which wants to set the magnetization direction parallel to the H effective or just magnetic field, has to be perpendicular to both magnetization and its derivative. And we somewhat can say with intuition that it should be proportional to the derivative of the magnetic magnetization as well. And then we can write this phenomenological equation of Gilbert damping. And by phenomenological, we mean, of course, that we just measure and observe this value instead of investigating how spin-orbit coupling forms it. In micromagnetics, all of these constants are actually phenomenological. We don't delve into theories of them, quantum mechanical theories of them. But this one is phenomenological outside of these studies too, I mean, in most cases. Now let's generalize furthermore by adding the Slonczewski term of spin transfer torque, which is of utmost importance in many spintronic applications, to arrive at the so to say governing equation of all spintronics, which is LLGS equation. And this term, I'm not going to write the components of this term, but cannot again change the magnitude of a magnetization in a dV volume. It does, however, change its direction and perhaps reverses its stable state, as we want to do in many applications, like writing to a FRAM memory cell. And now we have some useful equations. We can just integrate in time this magnetization vector at any point by software. It seems easy now. But we don't know what causes this H. Now, by the way, we should have this notion of macrospins being considered here. Remember this transition. I'm transforming from a single magnetic moment to a magnetization in a certain dV volume. And while doing that, we assume that all the spins in that dV, in that particular region in the space, are pointing to each other and are coupled to each other so strongly that they even precess together. This is the case for ferromagnets, where neighboring spins are very strongly coupled using exchange interaction. Exchange interaction is the strongest of all interactions we consider here. And we assume they are precessing together, and therefore a macrospin, which has the magnetic moment sum of the constituting spins, and also an angular momentum constituting of some of the spin angular momentums of all the electrons within them. And now let's see what effects we consider while investigating the dynamics of a spin or a macrospin in a lattice. Now remember the exchange interaction between two spins. They do not have to be neighboring, but when they are neighboring, this is a lot higher. And also when we assume only neighboring spins are acting on each other, we arrive at really successful models. And now, when we try to calculate this exchange interactions for macrospins, which correspond to all of the moment-forming spins in an area in a ferromagnet, we fail to use this formula to get the energy between, for example, this region and this region. We could maybe use the assume that there is discontinuity in the interface between two areas, and that all the energy happens in the interface, but it is not a really good model. For that, we develop a really clever model and write the energy of exchange interaction in terms of derivatives of the magnetization in time. And now, from now on, as a side note, we will use a more standard notation, which denotes case M that we use for magnetic moments until now as reduced magnetization. This does make a sense because in most cases, its magnitude is going to be just 1. As defined here, it's always 1, of course. But in a ferromagnet, we will see that all the local magnetizations are equal to the saturation magnetization of that ferromagnet. And now we define the model as such, but it seems really unrelated to this equation here. In order to make a simple, actually rather simple connection between these two, I drew here this model. Let's take two spins, neighboring spins, S1 and S2 vectors, and try to calculate their exchange energy. And in order to find this exchange energy, we should calculate, of course, in a simple sense. Actually, these are wave functions, of course, but S1 dot product, S2, which is, of course, their magnitudes are the same, cosine theta. And cosine theta here can be thought as, because neighboring spins in a ferromagnet are all parallel to each other. And even these domains, by domains I mean macrospins, are almost parallel to each other. So we can say this angle is really small, and that the difference between these two loci contributes to the dE as such. And we can make a simple connection here using this model, and one can sit down and go on to calculate it precisely, but here it's enough to give the point I would like to give. Now next, magnetocrystalline anisotropy energy. It's caused by the orientations of the crystal, and there are many types of it, so I didn't go on to write all types of them as a list here. But in general, the energy depends on the direction of a local magnetization with respect to the crystal axis. This is the most simple definition. Because the individual spins are not important in this magnetocrystalline anisotropy energy, but which direction they point to does really matter. It's really easy to integrate it into our micromagnetic micromagnetic model, which gives us precisely what direction the spins in a given region point. And next effect is the magnetizing field. This is probably the hardest one to calculate in micromagnetics, because the best way to model a demagnetizing field is to use mathematical magnetic charges, as in the CGS point of view to magnetism. And to do that, we need to calculate the divergence of the magnetization vector. This is an easy thing to do, but then when we find the distribution of magnetic charges in the volume, and problematically at the surfaces, because at the surface this volume density goes to infinity and there forms a finite surface density of charges in the boundary conditions, is another problem. And because this is dispersed everywhere, just to calculate the demagnetizing field at a given point in the device, we need to take into account many, if not all, of the neighboring cells' magnetic charges, which increases complexity drastically. And this is the single most expensive thing to calculate I've encountered in micromagnetics. And next we have Zeeman Energy, which is the easiest because we just give the software the external magnetic field, and then the micromagnetic software calculates the local magnetization vector at that instance of time, and just multiplying them gives an energy. But now we considered many forms of energy that have to be taken into account in micromagnetics. And we also gave the dynamic equation, governing equation in micromagnetics. And how we merge them is by using effective fields. I said that whatever causes this H field acting on a spin, we don't care. But now we care about it. The thing is, this is quite different. It's going to turn out to be quite different H field than we are going to calculate using classical electromagnetic theory, which is the average in the atomic volumes. But we need to find the exact value, the exact quantity of H vector that is acting on the spin itself in its own orbital. And in order to do that, because we know the energy associated with other magnetic phenomena, and all of their energies relate to the are applied to a magnetic moment in the same way a magnetic field does, that is by a dot product, we can define their respective derivatives as some effective field contributions. So there's an effective field caused by the exchange interaction, which is many orders of magnitude higher than any magnetic field we'll encounter. And then there is one from anisotropy, and there's simply, we gave this to the software, and another one from the Demagnetizing Field. We sum them up and get what we call H effective. And this is the H that is going to be used in every iteration of the LLGS equation in micromagnetics. Now, we come to the limitations of classical or shall I say canonical micromagnetic models. First of all, the temperature dependence is a limitation. As I mentioned, some more advanced software takes into account temperature effects, but temperature effect manifests itself basically in two ways. One of them is the change in saturation magnetization. This is an idealistic model that we made in one of the lectures. And this can be modeled kind of deterministically without complicating the simulation a lot. But random disturbances in the resulting structure that will be caused by the temperature cannot be determined deterministically. In order to determine what effect random distortions of temperature are going to have on micromagnetic configurations, we should have some fluctuating H effective or employ some Markov chain approaches. There are many studies related to them, and it would be really exciting to try to implement one of them, I guess. And just as we talked about this, we see here a really advanced form of simulation in which random distortions caused by temperature are practically visible. These structures seem really idealistic. What I mean is it could be a result of an ordinary differential equation, for example. But here we see some chaotic models. And what I wanted to talk in reality in this slide was additional effects that some simpler micromagnetic software packages may be lacking. These include Dzialushinsky-Moriya interaction, which is the basic reason for these fancy skyrmions are formed. The x-axis here is the strength of this interaction, surface DMI interaction, and also magnetoelastic energy and many other forms of energies can be added to the basic model. These are rather easy ones to incorporate into micromagnetic models, and I guess they are going to be contributing to the H effective field in terms of their own energy values. And here the example we see is from Karakash and others, where and others include our group and the Italian group I mentioned. And now let's come to some practical implementations, some previous implementations of micromagnetic techniques. First, let's discuss the practical considerations while implementing such software. First of all comes complexity. Complexity is not a great issue as long as the N, which is number of cells, number of kind of macrospins that we define, aren't really huge. But this number scales in a really bad manner with respect to the size of the problem, because it's proportional to the volume of the material being investigated. But other operations, like iterating through LLGS equation or finding the exchange interaction, involve just an addition or a derivation, for which finite difference method is used. I should note that. And these do not contribute much to the complexity. But for calculating the magnetizing field, remember, we have to add contributions from many different magnetic charge densities located around the volume. So it adds a lot to the complexity. Now, the cell size, determination of the cell size is a great issue here. And the key here is that we want to ensure the continuum approximation still holds, which means that we have enough cells to predict the magnetic domains, such that the magnetic domains do not look distorted and they are moving in a continuous manner. Otherwise, our finite difference derivations will not work correctly and yield some results that will not be able to reproduce physically. And the way to test this is, of course, by showing that further reduction in the cell count doesn't change, or cell size doesn't change the results. So we are working at such a cell size that making it a little bit smaller or larger does not significantly affect the end result we calculate. This is how we should determine this. And also, of course, we cannot go down to atomic scale, of course. Then our macrospins will be actual spins, and I don't think that's a really good idea. And another practical issue is handling of boundary conditions. One problem is what I mentioned. While determining the H effective, we have magnetic charges on the surfaces that have the volume density that go to infinity. We don't want that, and actually floating points in computers are really good at handling them, because they can handle many orders of magnitudes, larger or smaller numbers with the same relative error. But a good program, a well-written software, should consider these effects. And other issues with boundary conditions include when we need to predict what is going to happen when such a medium we define is infinite, we may make use of periodic boundary conditions, which will converge into the behavior that is going to be observed in an infinite medium. But in other cases, boundary conditions are largely determined by the input, which includes the initial configuration of the magnetic system. Sorry for the interruption. Now we are going to continue with ready-to-use software packages that could be made to use in micromagnetic applications. First of them is OOMF, which is intended to be a very generic software package for micromagnetic applications. It's programmed primarily in C++, but built upon this software package for intercompatibility with Unix and other like Windows systems. And this has the emphasis on extensibility, and it intends to provide an standardized interface. And there are some newer packages today, like MuMax. MuMax is GPU accelerated, which means actually it's called a GPU, which is an emerging use of graphical processing units in the last decade. It means we exploit the ability to exploit the parallel processing capabilities of GPUs, which can make these simulations which only necessitate extreme numbers of floating point calculations, but no conditional operations, and multiply the speed of these executions by up to 1,000 times. And it's written by NVIDIA CUDA, which is the most popular GPU programming software. And only downside of it is that it only works with NVIDIA GPUs as far as I'm aware. And another thing with MuMax is that it has an HTML user interface. So in order to run the software, you need to connect to a website that you run locally, or that is run on a server that has strong GPUs and in which you want to run the simulation and want to check how it's going when you're at home. So it's a really useful package today. It's a more modern package. And then there is this interesting project by authors of much larger micromagnetic software suites, Save the Lines of NumPy. NumPy is a Python vector library that is widely used for scientific and similar calculations. And this project exploits the ability of NumPy and possible simplicity in micromagnetic applications by trying to write the whole simulation in just 70 useful lines. And I actually ran this code today. It took some 10 to 15 minutes to calculate the standard problem number 4, the famous benchmark problem for micromagnetic simulations. And when we set standard problem, there is this MuMac group, which defined many years ago some standard problems that are used for comparing the correctness of micromagnetic software suites. So if we want to decide to write a software of our own, the first code, the first simulation we are going to do is probably going to be this standard problem, and probably number 4. And the problem number 4, for example, is defined as such. This is an example for an input for a micromagnetic study. We only give some constants for exchange interaction strength, the saturation magnetization, anisotropy coefficients, and damping coefficient and gyromagnetic ratio. And this is again a typical scale, typical dimensions of micromagnetics problem. And the aim is to observe how the magnetization of such an object made of a virtual thermalloy is being switched from one side to the other. And this is all I would like to present. The studies I mentioned, references are listed here, and thanks for listening. Have a nice day.